Thanks for none. Thank you very much, and thanks for the invitation. I'm very happy to be here. It's such a nice conference. So yes, I'll tell you about the index for non-rigid subcategories. This is joint work with Fedele and in August, and I'm with Shao in London now. So yes, the index has been first introduced by a standard in the context of Affiliation categories, module categories, and then it's been brought to triangulate categories, cluster categories that we've just seen in the previous talk, and so on. And it's played a very important role in homological algebra and higher homological algebra as well. This generalization. One of the important things is that it's played a crucial role in the categorification of cluster algebras and obtaining cluster categories. So we've seen McKinnon in the previous talk. There was this cluster character map or Kader-Schaffner map, and the index also appears there and it plays a very important role. And one of the main properties it has is that it's additive on triangles up to some error term, and this plays a very important role, but don't worry too much about that. So let's start with maybe the classic index. And our aim is basically to then take it with respect to more general subcategories. We'll see in what sense. So the classic index is some elements in some Grothendieck group. So let's maybe recall what these are. So for this talk, C would be a skeletonally small additive category. So just a nice enough additive category. And then at some point it becomes triangulated. So the split Grothendieck group with respect to such a category, as maybe you all know, I don't know, it's the free abelian group on the isomorphism classes of the objects. And then we put some relations, very simple relations. We basically take some class on the classes of objects. If we take a direct sum, it has to be equal to the sum of the two, basically. So these are the sort of relations we put. And then if your category has more structure, so if it's triangulated, like in the previous talk, this is like the shift functor. So if it's triangulated, or if it's exact, or if it's a B and there is another corresponding definition, then you can define the Grothendieck group of these. And in this case, for triangulated, it will be, you take this split Grothendieck group we just saw, and then you add more relations. So you put one relation for each triangle. So these are the sub triangle. Let's see. And I'm not going to go in details on what triangulated category is, but you can think of it as some additive category with some nice autofunctor, sigma, and then some sets of triangles, which are complexes of this form, A to B to C, and then instead of going back to A, they go back to the shift of A. And they have nice, very nice, they follow very nice rules that in some sense make them similar to short exact sequences. And you can also define the Grothendieck group with respect to an exact category, or if you want an abelian one. An exact category comes with some class of short exact sequences, and here you would put the same relation, but instead of using triangles, you would use the short exact sequences in your exact or abelian category. So the very first index, so the index will always be some element in some Grothendieck group. And the very first index, which we'll actually won't look at very much today, but just for completeness, was by Slander, and here C would be mod R. So finally generated modules over some Noetherian ring. And this is, well, this is an abelian category. And then each element in here, M, has some minimal projective representation. So these are projective modules. And then the index of M is defined as the class of P0 minus the class of P1 in K0 of Proj of R. And this is an exact category, so I will actually, here we would actually need the corresponding definition for exact Grothendieck groups, but which I didn't write, but just for completeness. So this was the first index, and it has some nice properties. And then it comes the triangulated index, which was introduced by Halu. And you can think of C as a cluster category if you want. So like the ones Eleonora was telling us about. It can also work for slightly more general triangulated categories. But yeah. And then, as Eleonora was telling us, you can take some very nice subcategories, these cluster 15 categories. And just to recall, as we've been told just before, it's maximally rigid. This T is maximally rigid, where rigid means that x1 of anything in T comma anything in T is 0. And so in maximal with these properties, and X groups in triangulated categories are very nice. They're just some special spaces. So this is a bit easier to deal with if you want, but yes, this maximal with respect to this property. And then I also want to be able to approximate objects in C with objects in T. And so these categories need also to be recurring or retrograde definite. You might be more familiar with this term, which means that whenever I take an object in T, I can approximate it with something in T, in this sense that, so I have some object in T and some morphism, such that whenever I have some object in T going into C, there is a nice factorization, and then the dual of recurring, which is pre-enveloping, which I'm not going to write, but you can guess. And if you have both of these, it's called transfer definite. So if you look at cluster categories with finitely many decomposable objects, these come really for free once you have a maximally rigid object. But if you want to look at infinite ones, you have to be a bit more careful. And this is some extra condition you need. And then what happens in this next setting is that whenever I take some object in C, I can always create some approximation triangle where these two objects are in my cluster 15 category, and then the index of C with respect to my fixed cluster 15 is going to be like before, sort of, where instead of projectives, I use objects in T, and this is in P0 split of T this time. And again, this has some very nice properties. It's been used a lot in cluster categories and these categorifications. And there are, it's additive on triangles in C up to some error term that we can compute, and it has some very other nice properties. So some very nice properties that were proven. A lot of them were proven by the here. Okay, so this maybe is a bit more technical start, but we'll mainly look at this thing in some very nice combinatorial categories, which were the ones that also Eleonora mentioned before. So we can start with the classic cluster category, and then we look at these infinite ones, the accusatore and the trajectory, and we'll see what happens over there. And our main aim is to drop some assumptions. Instead of looking at cluster theory subcategories, we want something more general and see if we can still say that this index that we will create has nice properties. So I guess the first example is this cluster category of type AN that we also saw in the previous talk. And this, it's modeled by an M plus polygon. And then basically here, the composables corresponds to arcs in my M plus polygon. Two in the composables have non-zero x between them if and only if the corresponding arcs cross. And so what are the maximally rigid subcategories? They are, so the cluster fitting subcategories are just all of the triangulations of these angles. Because if I want a maximal collection of non-crossing arcs, this is going to be a triangulation, and this will correspond to this cluster fitting subcategories. Instead, you can look at this infinite version. And so we have this other arcs of 1. That's also Leonore briefly mentioned. And this is the discrete cluster category. We can determine, we can call it Pn. And the combinatorial model is going to be a disk with finite many accumulation points. So many, let's say n accumulation points. So for example, I could put 4. And then what happens is that between any two of these, I have a copy of my integers. So it's discrete in this sense. So in this case, I have 4 copies of my integers. And then it works quite similarly to the one before, but now we have some sort of an infinite behavior. So now the composables are still gonna correspond to arcs between non-accumulation points. So accumulation points are not points, they're just the other ones can in some sense to that. Then we still have that between two indecomposables, x1 between two indecomposables is non-zero. And if it's non-zero between two indecomposables, it's actually one-dimensional. If and only if the corresponding arcs cross, so A and B. So, for instance, there could be something like this, or also within the same interval. So if they cross, they have non-zero x group between them. And then, and this is a symmetric condition, of course, because if A and B cross, B and A also cross, and this is x1 BA is also non-zero in that case. So this is actually a tuple category. This symmetry is very connected to this tuple property. And then the cluster tilting subcategories correspond to certain triangulations, and I'm not going to go into details about which ones you need to discard. But the main problem is that some of the triangulations are not recurring, so or pre-enveloping. So you have to be careful. There'll still be all rigid. All the triangulations are still in sense with maximal collections of non-crossing arcs. So they're still going to be rigid, but they might not be recurring. They might not be pre-enveloping or either of them. So yeah, that one needs to be a bit more careful. So I guess from here one can start wondering, oh, what sort of subcategories can I define a sensible index for? And there's been few steps towards this. So my co-authors, Peter and Amit, have a previous paper where they dropped the maximal assumption. So they described the index with respect to rigid pre-covering subcategories. So you could look, for instance, at some of these triangulations that are only pre-covering but not pre-enveloping and use their index. Or you could use dissections that are not maximal and use their index. Or even you can go into other triangulations and look at that. But more cluster-like categories rose more recently, and so we can go to the other one that Eleonora also mentioned. Should that? This should go down. Okay, that's not a good idea. I'm not that far. Okay, let's do this. So we have this packet yielding complete cluster category. Okay, and this is complete discrete cluster category. So the idea is basically, the philosophy is that we want the accumulation points to become points in some sense. And how do we achieve it? I'm going to call this Tn bar. And the way this is obtained is by taking one of the Igusa-Todorov points with an even amount of accumulation points, and then we take the Verdier quotient with respect to some nice triangulated subcategory. And let me tell you maybe what happens if I start with C4. Before I had 4 accumulation points, all these capital Z over here. And then I have 4 intervals. And basically D is going to be, I look at alpha of these intervals and look at arcs that are just between points in this interval. And this is going to be, this will correspond to my D. And then, well, if you want, you can also think of the perp, but that's not, yeah, the perp in some sense. I mean, it's not going to be particularly relevant for this talk, but the perp, it's going to be this other subcategory. And then there's also going to be some arcs that correspond to things that are in either D or the perp. And then when I take the Verdier quotient, as one would expect from a quotient, I kill everything that's in D. So basically, I squish these 2 points together. And the same with the other one. And now I obtain T2 bar. And what happens is that, well, anything that was in D gets killed because it was just arcs between the points that I squished together. Anything that was in D perp doesn't change very much. And in some sense, D perp will correspond to a copy of the Igusa-Todorov category, but now with half of the points. But then I also get these weird extra arcs that basically squishing these together will give me some arcs between accumulation points or between an accumulation point and a normal point. So now I can describe what the objects and axes and everything is over here. And it's exactly what, well, in some sense, what would looks like. So these are still going to be arcs, also between accumulation points now. So accumulation points now are genuine points. And I can have arcs between 2 of them or between 1 of them and a normal thing. Then I have that X1 between 2 in the composables is non-zero. And again, it's going to be one-dimensional if it's non-zero, if and only if. And now it's slightly more complicated. So 3 cases can happen. A and B cross normally. So this is a normal crossing. Again, now the endpoints might be accumulation points, but a genuine crossing. This should be higher. The other thing that can happen is that I have 2 accumulation points and A is equal to B. So this is a bit weird. Or finally, something that's not very symmetric anymore. And now I need to be careful. This is B, and this is A, in this order. So in this case, x1 between A and B is non-zero, but x1 between B and A will be 0. So this category is still a very nice triangulated category, but has lost some of the properties we had before. And for instance, it's not Stucalabia anymore, and it actually doesn't have a serpunctor at all. But it's still a very nice combinatorial category. So the main reason why we started looking into this when we were studying the index for non-rigid subcategories is that now most of the time relations are not rigid anymore. So again, still a triangulation will be a maximum collection of non-crossing X, but now stuff like this produces, there's still no crossing in the usual sense, but they produce some non-zero X group. So it's not going to correspond to a rigid subcategory. So for example, you could look at just, C1 bar, for instance, that's enough, and just the fountain out of the only accumulation point, and this is very far from being rigid, because, there is an extension between any two of these in one direction, for instance. The cluster fitting subcategories still exist, but they're a very limited amount of triangulations. So these are going to be triangulations with two-sided functions, fountains. At accumulation points. And by this, I really mean whenever I have an accumulation point, I need some other points, some other normal point here, and then overall some behavior like this. And I mean, locally something different could happen, but overall this has to happen. And then one single arc going there, so that I guarantee this is still rigid. I could still have a rigid object if I had something that is called a leapfrog that sort of approaches something like this, but this would not be recovering or pre-enveloping, I think, as well. So we also want to avoid that. So at each accumulation point, we need exactly some fountain going into that and value reduction. And this is the only way you achieve cluster fitting subcategories. But there are way more triangulations available, and lots of them will be free-covering. So for example, this one is a free-covering subcategory, but it's very far from being rigid. And so what we wanted to study was the index with respect to free-covering non-rigid subcategories. And again, you can do this in more general triangulation categories. And this is our work. And see what sort of properties are still true. So here we want C to be some carefully small, idempotent, complete triangulated category, so some nice enough triangulated category. One example you can have in mind is just this completed discrete cluster category, but it's not necessarily just that. And then some additive subcategory, which is also recurring in the sense that I said before. So basically, we can define an index, and this will still have the very nice property of being additive on triangles up to some error term. So how do we do this? So now it becomes, again, a bit technical in some sense. So the first step is that you need to view you need to put an triangulated structure on this triangulated category. So it's something a bit technical. So if you have a triangulated category, as we said before, it's some additive category with some autofunctor and some list of triangles. And you can always see it as what is called a triangulated category. And this is some work by Nakaka and Falou. So triangulated categories are way more general than just this. But one way of getting familiar into them, I guess, is that there are simultaneous generalization of exact category and triangulated categories. And they're additive categories. They come with some nice B-additive functor, which plays the role of X in exact or triangulated categories, and then some realization of sequences in some sense of triangles. So if you actually start with a triangulated, the way to view it, so without losing any information, to view it as an triangulated category is that E is exactly what we've called X so far. So, and this also works with a median, of course, but when you're focusing on this, and this is some additive factor. And then this S is a realization that takes some elements C from C to sigma A in this X1 or in here or generally, and it gives what we call a realization. So it's maybe I should change the word. So this is the Yoneda equivalence class of the corresponding triangle in my triangulated category. So yes, this is a bit technical, but at the moment we're just rephrasing the triangulated category without losing any of its information. But one can look at different triangulated structures on the same category. Just like when you can look at the different exact structures on a given abelian category, for example. So this is the realization, and ABC, maybe I'll write it here since it's just A, D, C, A is a distinguished triangle. So in this case, you're just literally just keeping all of the triangulated structure and rephrasing it in triangulated terms. But one other thing that you can do is, instead of taking this B-additive functor to be all of X, if you choose a nice enough subfunctor, you still get what is called an triangulated category. So it would still be an additive category with some other different B-additive functor and some realization. And so this is one way of creating new triangulated structures on this. And this is what we need to do for our index. So we take a B-additive subfunctor of this X functor, and it's going to be the morphism in here, so in this X1 group from C to A, with the property that whenever I take some X in my fixed subcategory X, so whenever I have this is 0. This is that I'm keeping. And this is some nice B-additive subfunctor of E or X1 in my triangulated category. And then, so this is a construction that was actually already proved by Action and Nakaoka, which says that if you take the same C with this EX, and then the realization restricted to this subfunctor, so I discard some triangles and I only keep the triangles with this corresponding to this C's in the X that I'm taking. This is still an extrangulated category. And this is going to be the correct category to look at our index amount. So we can define the Grothendieck group now with respect to this extrangulated category, or in more generally with respect to an extrangulated category. And this is exactly working just like before. So you take the split Grothendieck group on C, and then you kill one, and you put one relation for each, not for each triangle in your category, but for each triangle that you're saving in this construction. So you put one relation for each triangle such that C is in EX. And we call them sometimes EX triangles. So this, we're putting a bit less relations than in the Grothendieck group of the triangulated categories, but it's still something reasonable to do. And this is still a quotient of K0 of C, of course. And then we define the index with respect to X of some element in C as the element C in this Grothendieck group. So this, at first, you might say, well, this looks quite different than the index we defined before. But actually, when X is cluster tilting, so in the special case of cluster tilting subcategories, because our X is still an additive subcategory that's recovering, and so cluster tilting subcategory are a very special subset of these X's we're looking at. Then what happens is that K0 TEX will actually be isomorphic to the split Grothendieck group of X, and under this isomorphism, this class is sent to the index as defined before. So taking a plastic index in here. So somehow when you take the special case, you obtain exactly the index you would like, but this is more general. And for general triangulated categories, we can say that some of the very important properties of the index are still true. And in particular, the one I've been talking about is additivity one. So this is true in general for triangulated idempotent complete categories. So I mentioned this. But then in the packet-Hilbrim category, it becomes even nicer. So the index, our index, is still additive on triangles of C up to error term. And I'm not going to go in details about what this error term is. It's a bit complicated, but the important thing is that we can compute it. And up to this error term, the index is that. So let me tell you how much nicer it becomes if you look at this special category. So you can look at this pre-covering triangulations. And even if they're not rigid, you can now compute the index, and it's going to have some very nice properties. So a triangulation, so a fun triangulation is a triangulation without leapfrogs, infinite leapfrogs. And the leapfrogs were the things I was telling you about before, which cause the subcategory not to be recovered. So somehow again, find things, something like a triangulation here could happen, but I want to avoid so this going back and forth as a limit around the affiliation point. So then we can prove that these are exactly the triangulations that correspond to pre-covering subcategories. So let X correspond to a triangulation. Of this with the combination points that are now points. Then the following are equivalent. And this X is a fun triangulation. X is a pre-covering subcategory. And actually, also X is a pre-enveloping, which we don't particularly care in this talk, but it's also true, which is quite nice. So all the triangulations that correspond to pre-covering subcategories are exactly these fun triangulations so triangulations of any sort that don't have this infinite leapfrogs, but they could be non-rigid. So they could have multiple arcs going up out of this. They could be a complete fun, like in that example, or something more exotic. And then one very nice thing that happens in this case, just one last, right, these two last results. So if X corresponds to a fun triangulation, then for any object, we have some EX triangle. So a triangle that's also one of the ones we say in our triangulated structure, that is basically the same concept as an approximation triangle that we saw at the very beginning of the talk, that existed always for cluster fitting subcategories. So x0 and x1 are in X, and somehow we can approximate our C with one of these EX triangles. And by EX triangle, I really mean that this map is in EX. That's fine. Okay, and once we have this, we can prove that there is an isomorphism between K0 Tn bar of EX and K0 split of X, which takes what we called the index. So under this isomorphism, the index of some object C was defined, which was defined like this by our definition, actually sent to this x1 minus x0, which was exactly what we would like to be into the triangulated case. So somehow it recovers, in some sense, this initial definition of what the index is. So in general, this doesn't work for a general triangulated category, but for these packet-yielding ones, if you choose X in this way, then the index is exactly what you would expect it to be in the split Grothendieck group of X. And we could also prove more properties, the vehicular properties in this context of this very special category. So I guess this is a nice stopping point.
Thank you very much for the nice talk. I'll start with a comment to give you some time to think about questions. So now index is defined for the completed one, and so if the Euler characters they can be defined for the infinite arcs, we have the CC map.
Yeah.
This category.
Yeah, we haven't tried to do that, but that would be nice.
Any more questions or comments?
And what was the new result actually came out?
The what, sorry?
The main result that you have here.
So I guess our main aim was to the fact that for general triangulated categories, this new index is additive on triangles up to some error term, and then that here it actually is what you would expect it to be, and some other results we could also bring from the vehicular ones is that the index distinguishes rigid objects as well. So this is still true, for example, in this context and some other.
Do you have a paper right now?
Yeah, it's a preprint at the moment.
Preprint. In archive, I see.
Yes, okay.
Mhm.
Not directly about index, but about cluster. So there was the notion of clustered structures according to births.
Cluster structure?
Cluster structures according to Uaniyama, Wrighton, and published one of them.
Okay.
And for that, you did not require X condition.
Okay.
It was required that you have clusters and that you have a mutation. And that mutation kind of follows the quivers, the way we mutate quivers, but it did not require
Rigidity.
rigidity.
Okay.
Okay. So I wonder if it is satisfied that, because also like when we did continuous cluster categories have the same burst cluster structure, but they are not
Rigid anymore.
they're not rigid.
Okay, we haven't, I'm not aware of that.
So
Yeah, maybe you can show me.
Yeah, it's not rigid, so I'm wondering.
Yeah, if somehow it coincides or it's related
Yeah.
somehow. Yeah, maybe we can talk more.
Yeah.
Yeah. Thank you.
Okay, maybe can you say something about the error term? Does it somehow measure like how?
So it's, yeah, I'm not, so it's very, so it's, you can build a homomorphism between the category mod, it's between K0 mod X and this protein D group. And then, so it's some functor of some sort. And then the error term is, you have to take the class of the image under the Yoneda extension restricted to X of some map. And this is the error term. So you have basically your triangle is something like this, with this C. And then you take this morphism, you have to compute the Yoneda functor restricted to X on this. Then you take the class of this image and then apply this functor, and this is your error. So we can describe it, but it's a bit of a complicated term.
Okay, maybe I missed, did you talk about how you use them?
No, we didn't
Oh, you didn't
look
look
at
at
simulation. No.
Okay, because I thought I was.
Yeah, no, we didn't actually look at it. We actually did all the paper without this cluster category with just for general triangulated categories, and then after a bit we realized this could be a nice application, and then we added a whole new flavor to the paper in a second month, but we didn't look at mutation.
One more question.
Yeah.
About the extra-annuated categories, if you take the derived category, and just chop it up.
Mm-hmm.
Let's
Like
say
for the cluster in the same
yeah,
way.
well,
Or-
you see, for cluster category, you take
wrap it.
orbit, but
Yeah.
you don't take orbit, you just cut it like this.
Okay,
Is that?
so if it's extension closed, it should be externalated, so I guess so, yes.
Okay.
Okay, let's thank Francesca for the science. Okay, we resume in, I will give you 5 more minutes, 25 minutes. We are.